Okay, so now we're going over applications of the dot and cross product. This is lesson 7.7. They've given us quite a few formulas here. I'm going to scroll down a bit so you can copy them as we talk about them. The first formula calculates work, okay? And that's work measured in joules. So our vector F is the force applied to an object in newtons. So this has to be set up in newtons. S is displacement of the object in meters. Okay. And we're going to get to a formula below that talks about R, and R is the length of the object being turned, or the radius. Okay, and that has to deal with torque, which is a question we're going to get with later. This W can also be broken down into vector F being the magnitude of vector F multiplied by cos theta, or vector S, which is the displacement of OA. So we're referring to this here. This would be our force. We would find the magnitude of this force and then multiply it by our cos theta. And then that again is multiplied by the distance, which is a scalar, how far the object is moved. So this would be the force being applied to the object sitting here, and this is how far the object moves over. Okay. Our second formula is cross product, and we're looking for the magnitude of cross product, or the absolute value, which is also equal to the magnitude of A times the magnitude of B times sine theta. And this is helpful when we're trying to solve the area of a parallelogram. Area of a parallelogram is equal to the magnitude of the cross product of vectors A and B. And the area of a triangle is equal to half of the magnitude of the cross product of A and B. Finally, torque. Torque was where I was talking about R. F is still the same. F still stands for the force applied to an object. But torque is our radius or length of an object, okay? And that torque can be calculated by the cross product of the length of the object cross the amount of force being applied to it, which is the same formula we had above. All right, same as this one here. And the magnitude of torque is the same idea of the area of a parallelogram, the magnitude of the length of the object cross the force it's being applied to. So a whole lot. Okay, I'll zoom in one more time. Yep. Talk about it after. Okay, we'll go back to those. Those are all in your textbook at the very end on page 414. Okay. First question we're going to deal with is using the dot product to calculate work. Okay. Since you're in your textbook, I'm not going to write this one out. But Mariana is pulling her daughter in a toboggan. I love these toboggan questions. Okay. So she's got a toboggan, and she's exerting a force of 40 newtons. Okay, so let's say that she's pulling her daughter with a rope. This is the horizontal. Obviously, the toboggan is going across the ground. The force she's applying is 40 newtons. This is example 1 on page 410. And the force she's applying is acting at a 24-degree angle with the ground. If Mariana pulls her child a distance of 100 meters, okay, so we're going to assume this is the 100 meters, how much work is done? Okay, so we have our toboggan. I'll draw it again. This time we'll try to set it up like a triangle. So we have our force being exerted, the distance traveled. So this would be considered our 40 newtons. This is our vector V, we'll call it, force lifting. And the area traveled, they've called H here in your example. Okay. Now, in order to calculate work, let's go back to that. We're talking about the force being applied. And the force is, remember, in newtons. Okay, so we're applying a force of 40 newtons, and it's times S, which is the distance traveled. Well, the distance traveled in this question is 100. Okay, but F itself, force being applied, is also a formula. Remember, that formula is the magnitude of F. Okay, so that's the vector itself. We have the magnitude, which is 40 newtons, cos theta. So that 24 degrees comes in handy. We actually have to calculate, before we can get into our work formula, we need to calculate the vector of the force, okay, which is the magnitude of the force multiplied by cos theta. Our distance we already have. This is distance pulled. Our distance pulled is 100 meters. So we can get to that. But we do, again, need to calculate the force. So the magnitude is 40 newtons multiplied by cos 24. Our force in this question would be 36.54 newtons. Okay. So in other words, the power she's using to pull forward, because it's at an angle, has been reduced. Even though she's using 40 newtons to pull it across, the toboggan is not technically being pulled parallel to 40 newtons. Okay, that's the idea here. She's losing a little bit of her power due to having it being pulled on an angle rather than directly across on the horizontal plane. So the work altogether, or the work used, is our 36.54 newtons multiplied by our meters. Okay, so remember, this is measured in newtons, this is measured in meters in all questions, and this is measured in joules. Our meters are 100 meters. So the work in joules is 3,000, is it? Yeah, 3,654 joules. That's not enough.
Don't we have to calculate the V first?
Say it again.
Why is the V